Hello, welcome to CSC 280, the Introduction to Cybersecurity, with today's topic to be modeling, and specifically we're going to be looking at threat modeling, at least from a high level. So what we have to acknowledge is the fact that when we design a system, we have to understand what it does. And so before we can design and build a system, we really have to think through that and make decisions about what we will be doing in this system and what we won't be doing in this system. In other words, we have to determine the scope of the system. Now, I keep on talking about a system, but before, of course, we can do that, we have to define it. And it turns out there is really no unambiguous way to define a system. But for our purposes, what we'll use as a definition is that a system is a structured, or at least a semi-structured collection of interacting people, artifacts, and processes. And so what we're talking about is a socio-technical system. We include the people who use it in our analysis and our models. We also acknowledge the fact that these people have to work according to a predefined process. And lastly, we're going to build stuff, the artifacts that are in line for the system, and hopefully we can reuse some of the work we may have done in the past. So a structured or a semi-structured collection of interacting people, artifacts, and processes. That's what we consider to be a system. It's a pretty broad definition, but we got to start somewhere, so why not this one? There's a couple of principles that we have to always keep in mind when we deal with systems. The first one is that all systems are part of a larger system. And for example, I might look at the registration system that we use at Adelphi University. But that is part of a larger student management system, which is part of a larger IT infrastructure, which is part of the university, which is located in Garden City, New York, which is located in the United States of America. That happens to be, for the most part at least, in North America. So as you can see, we can always scale up to the next model that engulfs the model that we are analyzing or designing. And that means that we have to determine what kind of interactions exist between the world around the model, around the system, and the system that we are dealing with. On the opposite side, we can also generally decompose a system into smaller subsystems. Of course, there's limits that physics puts on us, but practically, we have this student registration system, but we can really break that down, and we can say, well, there has to be a course catalog in there. There has to be a student record database in there. There has to be a mapping between the students and the courses. There has to be an instructor database, which is a mapping of assigning instructors to these courses. Maybe grading happens through there as well. And so all we can do is look at a bigger system and then start decomposing that into smaller subsystems, where of course each of that smaller subsystem is then part of the overall system, but most likely each of those smaller subsystems can be decomposed further as well. And that allows us to really switch levels of abstraction in our thinking, which is useful because that allows us to put things to the side that we don't want to have to worry about for now, and that will fit in the bigger picture at a later point. We also have to understand that as systems become more specialized, they become less flexible. So the more that I am going to tailor a system for a particular situation, the less flexible it becomes. Case in point, we are in the middle of the COVID-19 pandemic at the moment, and around us, many of the villages have decided to open their village pools, but ask people to register for them so that they know that there's not going to be an overpopulation and people can indeed socially distance. They didn't have systems to do that. What they often did was reuse online systems that could be used to do event booking, where basically each reservation slot is a new event. It's not very specialized, it does not work very well, but it works well enough for the situation at hand. Whereas our course registration system, which really is also an event registration system, would have been entailed, we would not have been able to adjust that easily to do the same thing, because it was a more specialized system. Also keep in mind that as systems are developed, new features will be added to it. Systems grow, and very rarely do they go the other direction and do they become smaller. So, very rarely do we see a system or a product that decides to deprecate functionality and not replace it. And as these systems grow, it typically means that overhead imposed by those systems grows faster than the system itself. Now, when a system grows and it starts doing more, maybe you need more power to run it, you need more people to operate it, and all of that typically grows faster than the system itself. And so all of these things taken into account, it basically means that as our systems grow, they become more complex. And as they become more complex, they become harder to understand and harder to control. Again, the same thing we've seen in the past. Security benefits from simplicity. But I'm telling you now that systems tend to become more complex, not simpler over time. Which means that almost inherently, as we design a system, it will become harder to defend as time goes on. So that's something that we have to keep in mind. Now, I can talk about systems all I want, and I spend a lot of my time doing that, but what we have to also keep in mind is that human language in many cases is used very imprecise, where I might talk about a system and its capabilities, but I actually don't unambiguously identify that. Anytime I talk to someone about my system, and whether it's an existing system that I already have or a new system that I'm building, I have to constantly verify that they understand what I'm saying and that we are operating based on the same assumptions. That's not always the case. Now, in order to make that level of shared understanding better, we create models, and specifically conceptual models. And so a conceptual model is a symbolic representation of the relevant aspects of the system. And in particular, the conceptual model does that without having to worry too much about physical and technical concerns. Yes, of course, we have to incorporate those as well, but let's first understand the system independent of its technology, and then we can start bringing in the technology and all the things that come with that. But the conceptual model does not address technology. So the model itself is that symbolic representation of the relevant aspects of the system. In other words, it's not a representation of all aspects of the system. We're going to focus only on those things that are important for the things that we are talking about now, and we're going to use some form of a well-defined and unambiguous notation to do that. Those could be mathematical formulas, those could be symbols, that could be text, but all of those in the end are still symbols, and we know what they mean. Once we have that conceptual model, we can use it for two things. One is we can now more easily communicate with someone else who also can study the model and really understand it. And we can build our understanding while we are communicating with someone else what the system does or should be doing. So the whole point of these conceptual model is that they facilitate our understanding and our ability to communicate, and we do that using some form of a representation language. In many cases, conceptual models are diagrams, but a diagram without context is just a picture, and that means it's hard to understand. The phrase is, a picture says more than 1,000 words is true, except what happens if you take those words away from the picture? All of a sudden it becomes a lot harder. Reference, for example, putting together IKEA furniture. What we want to do is, if we analyze systems or if we design systems, at least to the extent that we need them, is to create these models, which are often diagrams. And it has to be comprehensible, has to be complete enough for our purposes. as agile development is becoming more and more important, sometimes people think that means that they don't have to design their systems or to create these diagrams. And that's not what agile is all about. Agile is all about doing just enough design and just in time, not necessarily do everything up front or don't do anything at all. So we do want to have some form of design documentation in place, if anything, that we can refer to it later on to verify that our design actually meets what we set out to build. So what we're looking for is to create a model that contains textual descriptions to provide context, but also those diagrams with their labels. And so readability is everything. In cybersecurity, we create models, or we could create models, for a wide range of reasons. And unfortunately, too many organizations and too many people think of modeling as overhead, and more specifically as unnecessary overhead. And as a result, they never go through the exercise. And even though individual people in the organization might believe that they have a good understanding of what their systems landscape looks like, very rarely is that accurate, and also not compatible. So different practitioners in cybersecurity can use models for different reasons. For example, if you're a software developer, you can use it to improve your software security by looking at, for example, let's model all the places where my software takes in external data. And anywhere that I have in external data, I have to do data validation and data scrubbing. The model could help us understand all of those places that we actually find information into our system. If we have a good model that is an accurate representation, a quality assurance team can use it to go identify where they should be testing. Penetration testers, which really are some form of quality assurance as well, could do the same. If I'm dealing with an incident, it's one of the first things we always do in terms of incident response is trying to understand what happened. If we have a model, a map if you want, of the systems that were affected and the ways in which they work, that would greatly speed up effective incident response. So having those maps or those diagrams is really helpful there. And there are all kinds of other reasons why we want to do this. The good guys can benefit from having models, but unfortunately so do the bad guys. So if you basically have a complete blueprint to what your system looks like and a bad guy gets their hands on it, that's an issue. So you really want to make sure that once you start embracing modeling, you do it in a way that you protect those models as maybe your highest prize target owned by a cybersecurity team. So let's take a look at a model here. Alice and Bob want to exchange information. Eve wants to figure out what they're talking about. Now Alice is at home when she sends email from her Google account. Bob's email address is with Yahoo, and when he checks his email, he looks at it on his phone, but he also checks it when he gets to a hotel room. What you see below is a symbolic representation. You see Alice and Bob clearly identified. We see Eve. We see Yahoo and Google represented there. We see home and email symbols. We see mobile devices and a hotel. All of the components are there, and we see lines with colors and arrows and magnifying glasses, and all those things are present in this model. But the question is this a good model? And I would argue no, it's not. It might be an interesting first step in identifying what's going on here, but it's not a model that anyone can understand if they don't have the right context with it. Also, we had no clear goal when we put together this model, and as a result, it doesn't really serve a clear purpose. We didn't have a level of abstraction. We did not use unambiguous symbols. There was no clear notation. There were a whole bunch of things wrong with this model. And so the question is, a picture does not make a model. A model has more than just a picture. Let's see if we can do this better. One of the older mechanisms for data modeling in particular is called the data flow diagram. And the data flow diagram means to model data in motion as it flows through an organization's systems. Where does the data go? Who interacts with them? What do they do with that data? And of course, all of those are important questions for a cybersecurity person to ask, because in the end, many of our intrusions are after data. The data flow diagram notation is really simple. We have a rectangle. We have an oval. We have two parallel lines. And we have an arrow. And that's it. Those are all the primitives we have. So what do they mean? It's a good question. The first one is the terminal. The terminal is a connection point between our system and the environment to which it belongs or with which it interacts. The whole point that the terminal is not part of the system. It's a connection point into or out of the system. And that's the rectangle. The oval is a process, and a process is something that makes information move, at least from this perspective. Remember when we talked about modeling, we talked about the relevant aspects, and here we are modeling how data moves. Data cannot move unless a process makes it move. And that means that a process needs to have a name, otherwise I don't know what I'm talking about. And that name should typically be a verb-noun combination. So create course, for example. Delete user, that kind of stuff. The process needs to have arrows going in and arrows going out. The arrow is directional. It's a direction of data flow. And the arrow should be labeled with the nature of the data that is flowing. If I see a process that only has arrows going in, only has arrows going out, or even worse, no arrows at all, I really have to scratch myself on my head and say, is this really a process? Am I modeling this correctly? And so I could have a process that says, well, okay, let's register for a class. And so to go in would be a student's preference to register for a particular class. Also going into that process might be, okay, which classes are available? And out might come an actual course registration. So that would be a good course, a good process. So we've seen the rectangles as the terminals. We've seen the arrows as the data flows. And we've seen the ovals as the processes. That leaves us with the parallel lines, and that's called a data store. That's the place where data hangs out. It's a decoupling point. Again, data does not just get spontaneously created. It needs to come from somewhere. So there's a process that will have to put the data into that data store. So for example, we see the create course process that puts courses into the courses data store. But we can't stuff stuff into a data store and never take it out. Nothing has infinite storage, even though it might seem like that occasionally. So I also want to make sure that stuff is coming out of my data store again, data. And we see that in the registrations, for example, where we put new course registrations in the data store, but at some point in time, another process pulls that out again when they check, for example, a student's roster or a faculty member's roster. And so when I do that, I have clearly defined meanings for all of the symbols in my map, and I can create a map of how data moves around. There's some rules. Like I said, a data flow must connect to at least one process. Black holes are those data stores that have data going in but nothing coming out. They're not allowed. And miracles are things that spontaneously generate data without anything going in the first place. That's also not allowed. When I apply those rules to my models, it's interesting to see what you end up with. But we can use those models for threat modeling. We can use this model now to figure out what kind of data is present in my system, who interacts with that data, where does that data move around across my system. So all of those points of analysis are potential vulnerabilities. And so I can use that to identify what vulnerabilities there might be present in my system, and I can go check the system to see if they're actually there. Keep in mind, threat modeling is a tool. It's not a solution. If someone tells you that threat modeling will solve all your problems, that's silly. That's saying like a screwdriver will solve all your issues. It depends on how you use the tool, and if you don't use the tool well or effective, it's not going to help you at all. Threat modeling is hard. Modeling in general is hard, and we'll do some exercises in class to prove that to you. But harder than that is, even if you know how to create a model, you have to maintain the model as you go forward. Systems constantly change. The environment constantly changes, and both of those changes have to be reflected onto your models, because a model that is not in sync with reality is kind of a useless model. In this particular case, we used the simple data flow diagram methods, but there are more advanced versions of threat modeling. But in many cases, why make it harder than it needs to be? The DFD already can reveal so much information. There's really no reason to go deeper than that. When we deal with cybersecurity and threat modeling, we have to understand that computers are used for different things. So, for example, sometimes computers are targeted because they have computational capabilities. I want to mine bitcoins, for example. So I want to have access to as many computers as I can to use their CPUs or their GPUs to calculate these bitcoin blocks. Or I might have my hands on all kinds of documentation or imagery that I don't want people to be able to find on my own computer. If that's the case, I want to stash it on someone else's computer, and preferably when law enforcement comes banging on the door, they're not banging on my door, but they're banging on the door of the person on whose computer I stored that data. Or I might want to use those computers for their ability to communicate. For example, I may want to run a large-scale phishing campaign. If I do that on my own computer, again, law enforcement will come banging on my door, and I'd rather not have that be the case. So, if we create models and we use those models appropriately, we could analyze those models from these perspectives.